Welcome back to our ongoing discussion on other formulas. Last time we'd pretty much wrapped up everything there was to say about double angles and half angle formulas. I had just a little bit left to mention about the tangent of a half angle, and I'll go ahead and do that. And then we will get into other formulas. So first thing I want to do is go ahead and wrap up half angle formulas for tangent. It starts fairly innocuously enough, right? It's tangent sine over cosine, so with some substitution that's going to be root 1 minus cosine u over 2 all over root 1 plus cosine u over 2. So the 2's will cancel there, leaving you just with one big square root 1 minus cosine u over 1 plus cosine u. And again, the plus or minus just depends on if you're in the first, second, third, or fourth quadrant. Depending on what quadrant you're in, that's what tangent needs to come out to be, right? Alright, well, going from here to finally ending up in the box, one thing you have to do is be kind of clever. You multiply by 1, which in this case is going to be 1 plus cosine u over 1 plus cosine u. That turns the numerator into something that's going to eventually simplify to be sine squared of u, right? 1 minus cosine squared is sine squared. And in the denominator, I also have a perfect square. So applying the square root, that's just going to be sine u and 1 plus cosine u. But really, you just have to pick the correct SIGN sign, right? The sign you pick at the end of this is either positive or negative, depending on if all of this mess is in the first or second or third or fourth quadrants. So you just treat all this to be positive, and then you pick your final sign at the end, your final SIGN sign, to be based on your quadrant. So that's why those absolute values are there, to remind you about that. Okay, enough about that. That's enough. Let's look at some other formulas. See, a very mathematical thing is to take something we know and to rewrite it as many ways as we possibly can to get as many other possible formulas that we could possibly use. So one thing we can do is take our sum and difference formulas and add them together. Right? If I've got sine of u plus v and sine of u minus v, and I add them together, if you look at the addition formulas, and go ahead and take a second to do that, if you look at the addition formulas for these, you'll see that one term of the sine of u plus v will cancel with one term of the sine of u minus v, leaving you 2 sine u cosine v. And then doing a little bit of rewriting, we actually have a product going to a sum. And you can do this for all 4 of these guys. Go ahead and take a minute to do that if you'd like. That's fine. But really, what you want to know is, where's all this going to come into play? That's a good question. I'll answer that later. Because we can also go from taking these formulas, make a substitution, specifically take u to be x plus y over 2, v to be x minus y over 2. So go ahead and start with one of these equations. Say this one. And substitute u for x plus y over 2, v for x minus y over 2. And so the sine u becomes sine of x plus y over 2. The cosine v becomes cosine of x minus y over 2. And with a little bit of rewriting, you will end up with this first summed product identity. So whenever you have the sine of some angle plus the sine of another angle, this is one single way to combine them. That might be useful, and actually we'll see why here in a second. And you can do that for the other 3, and if you really want to, you can go ahead and knock yourself out doing that. But here's kind of a motivation, or kind of a reason why you might care to do this, right? We have all these tools now, right? In this class, I will give you that formula sheet having the sum formulas, having the double angle, having the half angle, having the sum product, having the product sum, just having all of that spelled out for you. And it's now going to be your job to pick the right tool to do the right job. Do whichever's best. For instance, if I wanted to find the exact value of cosine of 255 degrees minus the cosine of 195 degrees, recognizing now that it's not the cosine of 60 degrees. That's not what it's going to be. One option we can go to find it exactly is find the cosine of 255, right? That's a sum formula situation. Cosine of 210 plus cosine of 45. Find the exact value of the cosine of 195, which is 150 plus 45. And then finally take the difference of those two exact values we found. We can do that. That is something available to us. But another option is saying, okay, I've got cosine of something minus cosine of something. I've got a formula that shows me exactly how to do that. This is tailor fit for this situation, right? Cosine of cosine minus cosine turns out to be minus 2 times the sine of the average times the sine of the midpoint, basically, right? The sum over 2 is an average, the difference over 2 is the midpoint. So you do that, and you would get negative 2 sine of 225 times the sine of 30. All in degrees, of course. And the exact value for sine of 225 is negative root 2 over 2. The exact value for sine of 30 degrees is 1/2. Put all that together, and you've got root 2 over 2. How about that? And compare that amount of work to what you would have had to do for 2 sum formulas and then the difference of that. Kind of like that. It's a lot less work. But it does require you to decide to use the right formula. And just one more. Kind of throw this in here because I like this one. I do. I do like this one because if I wanted to find the exact value of sine of arcsine of 1/4, it'd be a fourth, right? That wouldn't be so bad. Also, it's a typo, right? It's 1/5. I got 1/5 everywhere else here. So if it were sine of 2 arcsine of a fifth, it would be a fifth. Sorry about that. I'll fix that when I post this video, or when I post the PDF, right? I can't fix the video. I don't have video editing technology anyway. If it were sine arcsine 1/5, you'd get 1/5 out. But you aren't so lucky because of this 2 in here, right? I would get some angle for arcsine of 1/5, and then I would double that and then apply the sine. I can't just undo the arcsine and then double it and anything like that. So what I would have to do is apply the double angle formula, recognizing that sine of 2 theta, theta in this case is arcsine of 1/5. So it's 2 sine theta cosine theta. And well, sine of theta, right, sine of arcsine of a fifth is a fifth, great. But cosine of arcsine of a fifth is not anything you might readily recognize, right? You say, okay, 1/5, right? I've got 1 here, I've got 5 here. That would produce some angle having as its sine 1/5. So the arcsine of such a triangle would be 1/5. But to find the cosine of that angle for such a triangle, I need to find this length. And let's see here, that's going to be a squared plus b squared equals c squared. 25 squared equals 1 squared plus this value squared. So 25 minus 1 is b squared. So b has to be the square root of 25 minus 1. Call it 24. There you go. So that's how we get the cosine of the arcsine of a fifth is root 24 over 5. And it's all going to be positive because having this be my original value, I know by arcsine that theta is going to have to be in the first quadrant. So cosine is also going to be positive. And then finally, altogether, 2 times a fifth times root 24 over 5 does eventually boil down to be 4 root 6 over 25. Good times, right? As a curiosity, though, what would be the cosine of 2 arcsine? Actually, that's too bad. That's too rough. What would be the sine of 2 arc cosine of 1/5? You go ahead and finish that out for me, and I'll see you on the next video.